All right, welcome back. So, you've battled your way through second order differential equations, and you've pretty much mastered them. Well, you're ready for the next level. We're going to take everything you know and scale it up to tackle nth order equations. Now, I know they can look a little scary, but you're about to see it's actually a supernatural progression. Okay, let's get into it. So, over on the left, that should look really familiar, right? That's your standard second order linear equation. And on the right, that's where we're headed today, the nth order version. But look closely, it's the exact same structure. We just have, well, more derivative terms. We are not throwing out your old toolkit, not at all. We're just adding a couple of more powerful tools to it, building directly on what you already get. And the best part is that all the core theory you learned for second order stuff, it scales up perfectly. We just need to add two really essential new tools to our kit. First, we need a way to know if a unique solution even exists and, where we can find it. And second, we need a solid method to double check that our solution's building blocks are actually sound. Okay, tool number one. Imagine you had a blueprint that told you, before you even started building, whether a stable structure was even possible on a piece of land. Well, that's basically what this is. It's a theorem that gives us a guarantee. It tells us when and where a unique solution to our differential equation is certain to exist. And here it is, that blueprint I was talking about. So here's the deal, and this is the crucial part. As long as every single one of those coefficient functions, all your p's and that g of x term, are all continuous, no breaks, no gaps, across some interval, and your starting point, your x naught, is sitting inside that same interval, then you are absolutely guaranteed to find one and only one solution that works there. That's the theory, which is great. But how do we actually put this thing to work and find that safe interval for a real problem? Let's stop talking in the abstract and just walk through an example. It's really just a simple three-step process. First, and listen up because this is the step everyone messes up, you must get the equation into standard form. That just means the highest derivative, whatever it is, has to have a coefficient of 1. Isolate it. Second, you go on a hunt. You look for any spots where your coefficient functions might be discontinuous. And finally, you look at your initial condition and find the continuous interval that it lives in. Okay, check this out. Let's say we have the equation x minus 2 y triple prime plus y equals ln x with an initial condition at x equals 1. Step 1, standard form. We got to get that y triple prime by itself. So we divide the entire equation by x minus 2, and we get the form you see right here. Step 2, find the problems. Where does this thing break? Well, that ln x term tells us our solution can't exist for x less than or equal to 0. And that x minus 2 in the denominator? That means we have a huge problem at x equals 2. Step 3, where's our starting point? The problem spots are at 0 and 2. Our initial condition is at x equals 1, which is right in between them. So the largest continuous interval that contains our starting point is everything between 0 and 2. That is our guaranteed safe zone. Cool. So now we know where a solution can exist. But what's the solution actually made of? Well, these solutions are built from a set of functions. And just like the foundation of a house, those building blocks have to be solid. And more importantly, they need to be independent of each other, which brings us to our next big idea. So this is the textbook definition of linear independence. Let's break that down. In simple terms, it just means that no single function in your set can be built by mashing together the other ones. Each one is totally unique. It brings something new to the party. And this is so critical, because our final general solution is a combination of these functions. If one was just a rehash of the others, it would be redundant and we wouldn't be able to describe all the possible solutions. Okay, that definition is a little abstract, isn't it? It doesn't really give us something we can just calculate. So the question on everyone's mind is, how do I actually test a set of functions and prove they're linearly independent? Well, you're in luck, because there's an amazing tool designed for exactly this. And that amazing tool is called the Wronskian. It's a special kind of calculation. It's a determinant that you build from your functions and their derivatives. You can almost think of it like a machine. You feed your functions into it, you turn the crank, and it spits out a single number. And here's the magic trick. If that number isn't 0, your functions are independent. It's a clean, powerful, definitive test. All right, enough talk. Let's put this incredible tool to work. We're going to see how to build and calculate the Wronskian step by step using a really simple set of functions, 1x and x squared. So, to build the Wronskian, we're really just building a matrix. The first row is super easy. It's just our functions, 1, x, and x squared. For the second row, you just take the first derivative of everything in the row above it. So that's 0, 1, and 2x. Since we have three functions, we need a 3 by 3 matrix, which means we need to go one more level. The third row is the second derivatives, 0, 0, and 2. Simple as that. And here is the matrix we need to find the determinant of. But wait, take a look at its structure. See all those zeros in the bottom left? This is what's called an upper triangular matrix. And hey, if you remember anything from linear algebra, you know this is fantastic news because it makes calculating the determinant almost laughably easy. See, the determinant of a triangular matrix is just the product of the numbers on its main diagonal. That's it. So our Wronskian is just 1 times 2, which equals 2. And since 2 is definitely not 0, we have just mathematically proven that the functions 1, x, and x squared are in fact linearly independent. Job done. So there you have it, 2 brand new, powerful tools for your differential equations toolkit. You now know how to find the guaranteed interval where a unique solution has to exist, and you know how to use the Wronskian to prove that your foundational solutions are linearly independent. Which of course brings us to the biggest question of them all. It's great that we know how to check our building blocks, but how do we find those blocks in the first place? That is the next big challenge, and that's exactly what we'll tackle in our next explainer. Thanks for watching.